Welcome back, Algebra 3. We're in Lesson 33 today. We're going to talk a little bit about something a little bit easier to wrap our heads around, and that is a little bit of geometry. We're going to talk about quadrilaterals. So there are three types of quadrilaterals. Okay. The first type of quadrilateral is something like this, and that is a shape where you have no sides parallel. Okay. Then we have a shape like this, where you have one pair of sides that are parallel. Okay. Then we have shapes like this, where we have two sides, or I should say both pair of sides are parallel. So both pair of sides are parallel. So those are your three different types of quadrilaterals. Now within the pair of sides that has, or within the type that has one pair of sides parallel, we call that a trapezoid. That's what those types are called. All right, and then we have here where both pair of sides are parallel, we call that type a there's one R. I always get that mixed up. There's only one R. So parallelogram, which makes sense if you think of it. Parallelogram, everything's parallel to something, right? So this is parallel to this is parallel to this, and vice versa. So it makes sense that we would call that a parallelogram. I have no idea why the P is all the way over here. There we go. That's much better. So within the grouping of the parallelogram, we have some properties. All right. We have, picture if you will, I'm going to give us a Venn diagram here. In this group, we have rectangles. And rectangles have certain properties. That is not a rectangle. You draw a better rectangle for us. All right, that is a rectangle. Rectangle properties, all the corners have 90-degree angles. So that's our first property. All angles are 90 degrees. And our second property is that of the parallelogram. That, each pair of sides. So I guess that's really our first property, because that's the condition for it being a parallelogram. Being a rectangle means that all the angles are 90 degrees, and then the diagonals of the rectangle are equal. That is not a diagonal. So the diagonals are equal. This diagonal is equal to this diagonal. So the diagonals are equal, and diagonals bisect each other. So that means that if they're the equal length and they bisect one another, that this is congruent to this, which is congruent to this, which is congruent to this. So all four of those are going to be the same length, right? Okay, so there's your properties of rectangles. Now there's another category of parallelogram, and that is of a rhombus. Now, what makes a rhombus is that it is a parallelogram that has, let me adjust this a little bit. All right, that looks close. It is a parallelogram where you have two pairs of parallel sides, right? The opposite sides are parallel, but it also has this characteristic where this side is equal to this side, which is equal to this side, which is equal to this side. So first of all, you have the parallelogram conditions where you have the two pairs of parallel sides, but you also have the condition of all sides are congruent. Now, within the rectangle, you also have this side is congruent to this side, and this side is congruent to this side. So we could add number 4 down here and say that parallel sides are congruent. Okay. Here, all the sides are congruent. They're all the same length, regardless of whether they are parallel or not. 2, the diagonals are not equal to one another, but the diagonals bisect one another. So the diagonals still bisect, which means that this one is congruent to this one, and this one is congruent to this one, because this diagonal bisects this diagonal, and this diagonal bisects this diagonal, which the definition of bisecting means that we make two equal parts. We cut it in half. All right, the other property of a parallelogram, and both sides are parallel, but also this is relevant to all parallelograms, is that the angles along the same side equal 180 degrees. So what that means is, up here, not only are these sides parallel, but for this side, this angle and this angle, let's call this A and we'll call this B, A plus B will equal 180. That condition is also true for rectangles and rhombuses. So look at a rectangle. We have 90 degrees and 90 degrees on this same side. That's 180. Same thing here. 180, 180, 180. Okay? On a rhombus, it's the same property, right? You have two properties here. You have one property here. Right? So with this property, we have this one plus this one. It's going to be 180, but unlike the rectangle, they're not going to be the same degree of measure. We don't know what they are until we evaluate them. Okay? So that is a property that we have to look at. And the way it says it is that any pair of consecutive angles is supplementary, right? So consecutive angles is the same thing as angles along the same side. So that's another way to say that. That is the more geometric and mathematical way to say angles along the same side, consecutive angles. Angle 1, angle 2, angle 1, angle 2, angle 1, angle 2, angle 1, angle 2. When you add those pairs together, you're going to get supplementary angles. And we know that supplementary is equal to 180. Right? So that's your rule for that. All right, so we are understanding the majority of the properties here in regards to quadrilaterals and specifically parallelograms. Notice how I drew these two different distinct groups of parallelograms. There is an overlap right in here. And I bet you can guess what that overlap is. That overlap is squares. Squares have the characteristics of both rectangles and rhombuses in that. Let me draw a square. Lord, that's not a square. Let me adjust it. I need my grid so that I can draw a square better. Okay, that's close enough. So with a square, first of all, it is a parallelogram. All the sides, you have two pairs of parallel sides, as indicated here. Okay, so, and it also has consecutive angles along the same side are supplementary. Because, like the rectangles, they are all 90 degrees. All right. But like the rhombus, all the sides are congruent. So the four sides all have equal measure. So in a square, all sides, I don't know why I wrote that as one word, all sides are congruent. Number two, it's got the two pairs of parallel sides. Also, like the rectangle, the diagonals are congruent and the diagonals bisect. Okay. And the parallel sides, well, this, because all sides are congruent, all the parallel sides are congruent as well because they're all the same thing. So as a result, all angles are 90 degrees. Right? So you have the perpendicular sides, right? The sides are perpendicular to each other. So we can put that right here. That's what makes them 90 degrees. So all angles 90 degrees, which makes each side perpendicular to each other side. Then the diagonals here to here. This is going to be the same length as this, which makes this congruent to this, which makes this congruent to that and that. So all four are the same. So those are your properties, and that is, squares are unique in that they have all the properties of the rhombus and all the properties of the rectangle. They are a marriage between the two per se. So our first problem is 33.2. We're going to skip 33.1. 33.1 was just a proof to prove that diagonals of a rectangle are congruent. We're not going to do that. We know that. The properties tell us that. I'm not going to waste your time, right? 33.2, this is the actual problem, okay? It says the diagonals of a parallelogram are of unequal length. Which could that parallelogram be? All right, so the diagonals are not congruent. Which one is it if they're not congruent? This diagonal and this diagonal are not congruent, so it has to be a rhombus. We know these diagonals and these diagonals are congruent, so this one is not, so it is a rhombus. That's literally 33.2. 33.3, it says, the diagonals of a parallelogram are not perpendicular. If you look, that is another characteristic of a square here. If you look at your diagonals, they are perpendicular to one another. And it makes sense that they're perpendicular to one another because if you look, when we make the diagonal here, we bisect this angle. So this 90-degree angle becomes a 45. Well, the same thing happens here. This is a 45. So if this angle and this angle are 45, this has to be a 90 because 180 minus 90 is 90. So this remaining angle has to be 90 degrees. So these diagonals have to be perpendicular. So that's another quality we can add to the square, that the diagonals create perpendicular bisection. All right, so that's a 90-degree angle where the diagonals bisect. So very interesting. So if we are looking for the parallelogram where the bisected diagonals are not perpendicular to one another. That's what we're looking for. That's another property also of the rhombus, right? The diagonals are perpendicular to one another because they have the same length of side here. You've got you've got whatever this angle is and whatever this angle is. This equals 90. So half of this one and half of this one is going to equal this angle and this angle is equal to 180 because they're supplementary. So half of that and half of that is going to be 90, right? Because half of 180 is 90 when you put them together. So this one has to be perpendicular. This has to be 90 degrees in the center. So the diagonals are going to be perpendicular to one another in the rhombus as well. So that means that the rectangle is the only parallelogram that does not have perpendicular bisected diagonals. That's the answer. We're just looking at the properties and answering. So we have one more. It says given, I'm going to scroll this up a little bit. We don't really need what's at top anymore. Given a parallelogram whose diagonals are congruent, which of the following must be true? All right, 33.4, we have the diagonals are congruent, and it asks which of the following are true. A says all four sides are congruent, same length. B, diagonals are perpendicular. Bisectors, which we know all of the diagonals bisect, so I'm going to leave that word off. So the diagonals are perpendicular. And C, all four angles are 90 degrees. So all four angles are right angles. So which of the following, if the diagonals are congruent, which of the following are true? All right, so here we have congruent diagonals and all of the angles are 90 degrees. Congruent diagonals, all the angles are 90 degrees. So it could be a rectangle or a square. Right? In rectangles and squares, both of those conditions are true. Diagonals are congruent and hang on, where was I? Losing my mind. Diagonals are congruent. So rectangles or squares leaves out the rhombus. So if the diagonals are congruent, are all four sides congruent? Possibly. Yes, it is possible, because here we have all sides congruent where the diagonals are congruent. So yes, A could be true in squares. All right, so for squares, that is true. The diagonals are perpendicular bisectors of each other. So that would be rhombuses and squares, and that's it. So rhombuses, oh, actually, it can't be rhombuses because the diagonals are not congruent. So for the diagonals to be congruent, and then the diagonals are perpendicular, that's still just squares, right? And then all four angles of the parallelogram are right angles. So for all of these conditions to be true, it has to be. Now, if the diagonals are congruent, it could be a rectangle. It could be, but then all four sides wouldn't be the same. So for all of these conditions to be true, then it has to be a square. So I'm reading here, and for some reason it's got a drawing of a rhombus. Let me read why it's got a drawing of a rhombus. It says, first we note that a parallelogram whose diagonals are congruent must be a rectangle. Okay. All rectangles have diagonals that are congruent. Rectangles can have different dimensions. Not all four sides will be the same length. So A does not necessarily have to be true if B is true. Then the quadrilateral must be a rhombus, since B is a condition that guarantees a quadrilateral is a rhombus. However, a rhombus does not have diagonals that are congruent, as the following drawing, this drawing shows. The only choice left is C, which must be true, as all rectangles satisfy condition C, and that is that all four angles are right angles. So for some reason, I misunderstood the problem. It said, given a parallelogram whose diagonals are congruent, which of the following must be true? The diagonals are congruent. If the diagonals are congruent, I see what it's saying. If the diagonals are congruent, then this is all true. All four angles are 90-degree angles, and it doesn't matter whether it is a rectangle or a square. This is the only condition we care about. So rectangles and squares would be the one that goes with the diagonals being congruent. I was looking at all three of these to be made true, but this is the one that is true for rectangles. So I don't know why we need to do that. I really don't. It's one of the things in the book, and it's a little confusing. So let's talk about, we've talked about quadrilaterals. Let's talk about, or specifically we've talked about parallelogram quadrilaterals. Let's talk about trapezoid quadrilaterals now. I'm going to clear this. I tell you, before I clear it, make sure you have all the notes. And you know what? I wouldn't even worry about this one, because honestly, it's just logic, and it's not a proof. It's just asking some, hey, is this possible question unlike these two, which we were given specifics and we had to find the characteristic. So let's not worry about that one. Make sure you have all of this in your notebook, and then we're going to go ahead. I'm going to clear the page, rewind if you need to, and pause it so you can get any more notes you missed. Let's talk about trapezoids. So we know that a parallelogram is a four-sided polygon in which both pairs of opposite sides are parallel. A trapezoid is not. Trapezoid only has one side, one pair of sides that are parallel. So you can see here, this is A, B, C, D. We only have this side here and this side here. And what that means in regards to a trapezoid is that the height here is going to be the same between these sides. But that does not mean the length of the sides are going to always be the same, right? So the height is going to be different from the sides because there's an angle attached here. So you have the height between here and here because they're parallel. That's the definition of parallel. The distance remains the same. It's a constant all the way from end to end, and it's indefinite. So the height will be the same, but the length of these two slopey sides might be different from one another. They don't necessarily have to be congruent. The parallel sides are called bases. So this is a base, which is kind of weird because we tend to think that a base is the one on the bottom, but this is also a base. And the sides here, they're slopey. These are called legs. So that's the terminology for a trapezoid. You have the base and the base, and you have the legs and the legs. And then there is a line segment that connects the midpoints of the legs. So right in the middle here to right in the middle over here, this is called the median. And the median is the bisector of the legs. All right. Now, be aware, the median does not cut the area of the trapezoid in half because, you know, if just looking at it, you can tell this base is bigger than this base and the median is bigger than this base. So it's different here. However, there is a scale factor relationship. So remember that. An altitude of a trapezoid, or the height of a trapezoid, is any line segment that connects the bases together. So any line segment from here to here is called the height or the altitude. That's the other word for it, the altitude or the height. Now we can have multiple altitudes within a trapezoid if we draw multiple parallel lines. So if I draw a line parallel here, we could have an altitude from here to here. You know, that's just kind of common sense. If I draw another parallel line here, I can have an altitude from here to here. So, you know, that's a thing that might happen. And it creates a scale factor whenever we have parallel lines within a trapezoid. So the properties of a trapezoid are 1. The area of the trapezoid equals 1/2 the product of its bases. So you remember how we've been finding the area of a trapezoid? We've been kind of doing this dotted line here and making two triangles and here's the base and here's the base. And this is the height. Base times height divided by 2 for this triangle. Base times height divided by 2 for this triangle. Okay. That's what we're doing when we do this formula. This is just a faster way. And it's just base 1 plus base 2. And it is times the height or the altitude, however you want to say it, divided by 2. So it's the same thing. It's the same thing. Because think about our other formula has been base 1 times the height divided by 2 plus base 2 times the height divided by 2. You can see the similarities there, right? We're dividing the height by 2. We're just adding these two together. So base 1 plus base 2 times the height divided by 2 is the same thing as doing those two separate triangles. So that gives you a little bit of a shortcut in calculating the area of a trapezoid. Number 2, the median of a trapezoid is parallel to the bases. So the median, I cannot spell today. What in the world? The median, I'm still doing it. Why can I not make a D today? The median. There we go. Oh my goodness. The median of the trapezoid is parallel to the bases. Always, always, always. And its length, the median length, is half, the sum of the bases. So the median is equal to base 1 plus base 2 divided by 2. That is the length of the median. All right, so the length of the median. So there are your other properties of your trapezoid. Now, there are different types of trapezoids. This is not a regular trapezoid. A regular trapezoid is what we call an isosceles trapezoid. And if you, for just a minute, would picture an isosceles triangle, right, where the center of the triangle, the vertex of the top, is directly centered over the bottom here. If we were to cut that off at some point, like that, we would create an isosceles trapezoid. So we take an isosceles triangle, we cut the top off, and create an isosceles trapezoid. And what that means for us is that this side or this leg of the trapezoid is going to be congruent to this leg of the trapezoid. So these are going to have the same dimension here. So the properties of an isosceles trapezoid, we're going to add some things here. The number 1, I'm just going to write it here. Number 1, the lower base angles are congruent. So I'm going to label this A and D and B and C. So the measure of angle A would be congruent or equal to the measure of angle D. Number 2, the measure of angle B is going to equal the measure of angle C. Number 3, the diagonals are congruent. And that makes sense because we have the same height here. So this is congruent to this one. This diagonal here is going to be congruent to this diagonal here. So they do not bisect each other, but because they're congruent and because of the way they're made, this is going to be congruent to this, and this is going to be congruent to this. Okay? We know when we have, if these two sides are congruent, right, in a triangle, and this side is the same for this triangle as it is for this triangle, then that means that these third sides are going to be congruent as well. And if these diagonals, they don't bisect each other, but what they do is they create congruent parts. Wherever they intersect here, they cut each other at the same point. So this side is congruent to this length, and this length is congruent to this length. But from here to here, when you add this one together, it's going to be congruent to adding this one together. So those are your properties there. Make sure you look at that and get your congruency marks on there when you take your notes. All right, so let's do a quick problem, 33.5. So we are going to derive a general formula for the area of the trapezoid using this figure. This is not by any stretch an isosceles trapezoid. All right, we do have a height given here. And we see that we have, we can draw a little diagonal here and create the two triangles. Here's base 1, here's base 2. And we're deriving this is all we're doing. So we're saying if we take this base and and add them together, we know we've got two triangles. So we know that half of the base times the height plus half of base 2 times the height. That's going to give us the total area here. We can, looking at this, we can factor out half, and we can combine this to say base 1 plus base 2, right? We're factoring that out, times height. We're factoring out the height. So we can rewrite that as base 1 plus base 2 times the height is divided by 2. And that is the same thing we learned up here. That's how we got there, by factoring out the 1/2 and then factoring out the height to the end, which allows us to put all of this over 2 in fraction form. All right, so that's just proving how we get to the area. So let's do 33.6. Where is that? Here it is. 33.6. So we have some actual dimensions here. Here is our trapezoid. I'm just going to sketch it roughly. Our height from here to here, that's 10. The figure shown is a trapezoid whose area, the total area, is 175 centimeters square. Okay, we don't have to say area because we know that the exponent means area. This is x, this base is x, and this base is 2x plus 8. Dimensions aren't centimeters. Find x. So if this is our formula for the area, then what we need to do is this. We need to say 175 centimeters. Actually, no, I'm just going to leave it there. 175 centimeters square is equal to, we take the formula for the area of this trapezoid and we write it in. Base 1 plus base 2 times the height divided by 2. Right? So instead of dividing by 2, we're going to multiply both sides by 2. And when we multiply both sides by 2, that is going to give us 2 times 175. That's going to be 2 times 100 is 200, and 2 times 75 is 150. So 350 centimeters square is equal to base 1 plus base 2 times the height. Well, we know the height. We've been given the height. The height is 10. Let's put that in here. So I can divide both sides by 10. So that tells me that 35 centimeters is equal to base 1 plus base 2. Well, now I know what the values of base 1 and base 2 are. I have these problems here. So 35 centimeters is equal to x plus 2x plus 8. I'm going to move over just a little bit so we can continue the problem. So when I combine this, I get that 35 centimeters is equal to 3x plus 8. And I'm going to assume this is 8 centimeters. I'm going to subtract 8 from both sides. 35 minus 8 is going to be 27, potentially. Yeah, 27 centimeters is equal to 3x. Divide both sides by 3, and x is equal to 9 centimeters. So I can go back and find, I don't have to, I mean, my whole point of being was to find x. X is 9 centimeters to be exact. So I can go back and I can say that this one is equal to 9 centimeters. And 2x plus 8, that's going to be 18 plus 8. That's going to be 26 centimeters on this side. All right? And when I add 9 and 26, I get 35 centimeters times 10 is 350 centimeters, divided by 2 is 175 centimeters. So I've checked my work and the math works out. So we can see how to undo this appropriately, right? All right, so let's do another one. I'm going to erase all this because I'm running out of room. If you need to pause and take this down, do so. Clear the page, go back to the beginning. Here we go. So 33.7, and this is the last one. All right, here's our figure. This is 2x plus 2. This is A, this is B, this is C, and this is D. And we have a median here that is parallel. Trust me, all of these are parallel. My drawing is just kind of eh. This is E, and this is F. All right, this is 4x plus 1, and this one is 7x minus 2. So EF is the median of this trapezoid. We are going to find x. So one of the properties that we learned about trapezoids is that the median is parallel to the bases and its length is 1/2 the sum of the lengths of its bases. So that means that base 1 plus base 2 divided by 2 is equal to the median, right? We already discussed that. So this is what we're going to do. We are going to say base 1 plus base 2. So that's 2x plus 2 plus 7x minus 2 divided by 2 is equal to 4x plus 1. So we are going to find x. That is what we're supposed to do. All right, so 2x and 7x, that's 9x. Positive 2, negative 2, those cancel. So we have 9x over 2 is equal to 4x plus 1. All right, so what do we do when we have this fraction here times a variable? We multiply by the reciprocal on both sides. So that'd be 18 over 18. X would equal 2 times 4x, that'd be 8x plus 2 over 9. I'm going to multiply both sides by 9, so that's 9x is equal to 8x plus 2. I'm going to subtract 8x from both sides. X is equal to 2. That is our final answer. So that allows me to go in here and solve this. So this would be 4 plus 2, that'd be 6. This would be 8 plus 1, that'd be 9. This would be 14 minus 2, that would be 12. And if we look at this, 6 plus 12 is 18, right? Divided by 2 is 9. So that works out. Our math checks out. X is 2. And that is our final problem for lesson 33. Look at these properties. Look at these formulas. These formulas are things that you're going to need to write in the back of your book. Make sure you have them for reference on your back cover. As we go forward, you're going to have more of these problems, and you're going to have to solve for the length of the median. You're going to have to solve for x. You're going to have to know how to relate them one to the other in order to do all of that. All right. That's all we have for lesson 33. I will see you in lesson 34.